Hello, and welcome to today's episode of Rawkode Live. I am your host, Rawkode. Now, before we get started, I just want to cover a little bit of housekeeping. First, please subscribe to the YouTube channel. This helps other people find this content. My goal is to produce valuable learning materials for us all on the cloud native landscape, and I hope that you can subscribe and share that knowledge with us. Also, I want to encourage you to join our Discord channel where, if you have questions or you want to experiment or even suggest new technologies that we should cover, the Discord channel is the best place to do that. We've got a few hundred people in there now talking about cloud native Kubernetes and everything in between. Again, come and join us there. And I also want to thank my employer, Equinix Metal, who provide the time, resources, and everything else that allows me to do this as part of my job. So thank you, Equinix Metal. Feel free to check out that platform by using the code RAWKODELIVE. This will get you $50 in credit. That is roughly around 100 hours of compute on a modest instance. So take it, enjoy it, play with it. All right. Now, today we are going to be taking a look at Kubeflow, a open source program and technology that allows you to run machine learning workloads on Kubernetes. I am by no means an expert in machine learning. However, I am joined by Michael Tanenbaum, a Kubeflow maintainer, who's going to guide us through everything that we need to know to get started today. Hey, Michael, how are you? You there?
Hello. Yes, I am indeed here. I am both getting the live and the slightly delayed audio, so it's a little confusing for me.
I have done that so many times.
Yeah.
So
let me think. Perhaps I think if I resolve to use a single, perhaps not. What's your suggestion, David?
Do you have another tab open with the YouTube page?
Oh my goodness. Okay. Sorry.
Don't worry, like I said, I've done it before. Very easy done.
Well said. Okay. We resolved it. Thank you. All right, welcome thank you for welcoming me. Hello. Greetings. I'm here.
Awesome. That's the first hiccup done, right? Now that that's done, we can move on with nothing but glorious, successful demos here on in, and that's the way.
That's the only way I like to do business, David. Thanks. I presume you asked me to introduce myself, or
yeah, please feel free to tell us a little bit about you, and then we'll start talking about Kubeflow.
Sounds good. Okay. My name is Michael Tanenbaum. I am a principal solutions engineer in my day job at a company called Rawkode. We are one of the biggest contributors to open source Kubeflow, and my community participation is around the special interest group for on-premises deployments, where we are working to help make it easier for folks to deploy in their own data centers, and providing reference architectures, and particularly bare metal, because ML workflows are performance sensitive, and bare metal, no hypervisor, get it on out of there, is sort of a mantra that we're trying to encourage, and certainly there's lots of good reasons to do that. Security, cost, we can talk more about that if you're interested. But I live in New York City, so I'm speaking to you today from Red Hook, Brooklyn, and what else? And previously, I've been in the Kubernetes space for a long time. Before that, I was in the Mesos space. For any cloud native dinosaurs in the audience, I worked at Mesosphere for a couple of years as well. And I started my career as a junior developer working on analytics tools at the World Bank, and since then have done a million different things all around the software world. So I love software. And have ever since I was a little kid, and that's sort of what got me into it. I have no formal education, it should be noted, in anything related to computer science. I studied Chinese in college, but yeah, self-taught. It's one of the things I love about our industry, right? Is people don't really care what your diploma is, what's hanging on the wall. It's just, can you do the job that we need done today? And even if you can't, can you Google effectively? So.
I couldn't agree more. I have no formal education in computer science or computer engineering either. I'm a complete toe rag that managed to find his way into his first role and has just kept learning ever since. If it wasn't for Google, I probably wouldn't have this job. It definitely keeps me
Well,
keeps me from getting fired, I'm sure. All right.
cool.
Why don't we thank you for sharing all that. It's really nice to get a little bit of personal information as well as just a general overview of you. So that's awesome. Do you want to then tell us a little bit about Kubeflow? We can go straight into slides if you want to do that, or you can maybe give us a TLDR
Sure.
if you want.
Yeah. That sounds good. So speaking today, not from the position of not from my day job, but speaking about from the perspective of being a community member. So everything you'll see today is open source and available for folks to play around with. So yeah, I do have some slides. I think that might help illustrate a little bit about Kubeflow for folks who are new to the project. So there we go. Perfect. All right. The Kubeflow project is approximately, in a formal way, about 2 years old, 3 years old at this point, 2018. We are just coming up to the 1.3 release. And by just coming up to, I really mean just coming up to. I think the RC is being cut today. I should know. One of my colleagues here at Rawkode is the release manager. But I don't want to put him on the spot, right? As I said on the air that we were going to release RC, but yeah. Anyways, so Kubeflow 101, just as a broad intro, speaking from the perspective, I know your audience is well versed in the world of cloud native, so speaking to an educated audience about these sorts of tools here. So why was Kubeflow founded? Well, the reality is that today we don't really have great DevOps, SRE sorts of practices around machine learning workloads. They tend to be very snowflakey. They tend to be pets. They tend to have tremendous operations bottlenecks. After all, machine learning is a relatively new field. In my practice and in my day job, I see lots of folks who are coming to the machine learning world from more operations background. And then we see people who are coming from a data science, data engineering background now being tasked with, really bringing this into production, bringing this into a format where we can leverage the benefits of ML as opposed to at scale, right? At enterprise scale or organizational scale, for nonprofits and public sector folks who would like to use it. So the Kubeflow project was started to facilitate that. And it is, as we'll see in a minute, a collection of many different services, many different pieces of software. But the standardization around Kubernetes, which I would describe as an operating system for cloud native. Really, I mean, it's what we deploy distributed software onto, and you can be fairly certain at this point that anyone you need to move, any of your clients, any of your collaborators will also have Kubernetes. Anyone else in the ecosystem will have at least some Kubernetes in there available to them. It makes sense to put it on top of Kubernetes. So the project was started at Google. Obviously, Kubernetes would be the preference for them as well. And the Kubernetes scheduler is great at scheduling diverse workloads. So why not take advantage of it, right? So we've got the environment portability sorted, we've got the scheduling sorted, and we've got the scaling sorted, right? So leveraging containers and that paradigm for delivering scalable software. So that's the mission. All right. How do we help people get their hard work developing machine learning models to a place where we can provide a scalable and repeatable pathway to production? And maybe it makes sense to take just 1 second to talk about what we mean by production for a machine learning model. David, would you agree?
Yeah, go for it.
Okay. So what we mean by putting an ML model into production is going to sound very simplistic, probably to a lot of your listeners, in the sense that it's just an endpoint. It's just a service that we can send it some payload of information and get back another piece of information. That's all we need to do. The issue is, how do we automate as much of that process as possible while ensuring security, isolation, and so on. Does that make sense?
I do, yeah. Yeah, I'd say so.
An ML model at the end of the day is just a formula. It says, you give me, the pieces of information that I need, and I will give you back a guess. Could be a guess about, are we coming up to a stoplight? If you're a self-driving car, could be, does this person have a medical condition, which is the example we'll be looking at. So why Kubeflow? What was sort of the genesis of the reason, the genesis behind it? There are a lot of tools that can help in cloud native workflows. And the issue is that there's not really a good way to stitch them all together. So you can think of Kubeflow as an open ecosystem where you can put in the tools you want, take out the tools you don't, but you're guaranteed a degree of interoperability between all of the tools, and the base set of tools will always work together and cover really most use cases. Any questions on that? Make sense?
Yeah, I think I'm still with you. You've not lost me yet.
Okay, good. And this is from the Kubeflow 1.0 user survey from last year. The newest one, the 2021 version, will be coming out very shortly. Some of the issues around getting a model to production are, of course, the bottlenecks associated with, finding, the right operations people who can take the data scientist work output and then deploy it to production. But there's lots of other stuff too. Machine learning models are being used to enhance decision processes, some of which may have legal or compliance implications. Making a loan decision, for example, would be one of those. Making a hiring decision would be another. And so the more automation that we can get around documenting what the model is doing, why it produced a certain thing, and bringing that cost down, as well as time, is of great value, because there's lots more models that folks want to put into production, and 90% of them never get there. I saw a statistic fairly recently that said that for the average American bank, it's over $500,000 just in compliance costs to get a model into production. So
Damn.
lots of headache and costs there. And the general practice is that it takes a good 6 to 9 months to get a model into production. And for example, if you're let's pick an example. If you're a streaming video player and content producer, I certainly remember when Tiger King was all the rage. It is no longer the rage. So if I'm developing a recommendation engine using machine learning that helps viewers identify other shows that they might like to watch, other programming they might like to watch, it doesn't help me very much if my model that was trained 6 months ago gets deployed after that data is stale, right? So there's a notion of currency in machine learning models that doesn't exist outside of revving libraries and other stuff for software development more broadly. The data needs to be current. There's a declining return to the value of data as time goes on. So what's in the box? You're welcome for not including the meme. As I mentioned before, Kubeflow has a ton of different stuff in it. The data scientist or machine learning engineer or data engineer will be familiar with certain frameworks. TensorFlow, PyTorch, MXNet. Those will be familiar. They, of course, also have their fans and detractors and their lineage. PyTorch was developed by came out of Facebook, if I'm not mistaken. TensorFlow is from Google. MXNet is developed and promoted by AWS as an example. But they're all open source. And so this, you can think of the top of this diagram here as the interaction with the end user will interact with these libraries via some containerized environment. It could be Jupyter Notebook as an example. It could be VS Code. It could be RStudio. Lots of different ways to interact with the software stack proper. And the beauty of containers is that not only they come up very quickly, but also that, we can standardize on a set of common libraries, and then as we need to make adjustments, of course, layer on top of them. Under the covers, what we're also delivering as part of Kubeflow is a set of operators that relate. I'll focus down here to start. A set of operators that relate to the specific machine learning libraries. So let's take TF job operator as an example. So one of the great advantages of distributed computing is that things that would take forever on a single machine take longer when we're able to effectively chunk up that work and distribute it among many machines, right? That we can't make the computers any bigger, nor would we necessarily want to. And there, to Waleed's point, thanks for the comment. There are actually quite a few more that are very close to being ready for prime time. So stay tuned if you're interested in that. Definitely check that out. But how do these? What are these operators? Well, to quote my dear friend Jared Dillon, an operator is just a piece of software deployed with its own runbook for managing that software. In other words, a custom scheduler. You could think of it that way in some ways for these operators that you have here. And so what we're able to do is take our standard code that we would use TensorFlow or something like that, and very effectively using the operator along with the Kubernetes API, Kubernetes scheduler, distribute that across all of our resources. So if you're doing machine learning on huge amounts of data, you can take something that would take a week to train on a single machine. You can bring it down to half an hour, right? Just depends on the resources that you have available to you. So that's really where we see some of the efficiencies for folks, and one of the most exciting elements of the software stack. We have a Jupyter. It's a little bit of a misnomer. I think they're actually, the Notebooks working group is contemplating changing the name of it, but essentially a notebook or coding environment, web app and controller. We'll see that in a second. It's all self-service and supports securely injecting secrets into the environment, so you don't have plain text secrets floating around. Resource dependencies, does this coding environment need to have access to a GPU or some kind of special resource, some extended resource in Kubernetes, etc. We also have quite a few attendant core services that are necessary for productionizing machine learning workloads. Pipelines, for example. Folks may be familiar with tools such as Airflow, or others that provide directed acyclical graphs, DAGs as they're known, functionality, so that we can have retry logic, branching, all of that kind of stuff. Kubeflow Pipelines is built on top of Argo, you can see here, and interacts natively. So the beauty of the system working together is that all of these bits and pieces know how to talk to each other. There's a metadata store. So what did we do? There's a Kubeflow serving, which is built on top of Knative, that provides the ability to publish a model as an endpoint, right? So if I'm a data scientist, I don't really know that much about operations. I don't know really anything about Kubernetes, perhaps, and I still want to be able to start doing model deployments in a safe way. And so Kubeflow serving is built on top of Knative, as I mentioned, and leverages Istio's ability to segment traffic, as well as do things like canary deployments, blue-green, all of that kind of stuff. So if there's any language here that I'm using that you think folks might not be familiar with, I'm happy to dive into it. And then lastly, and this is super exciting also, automated hyperparameter tuning. So we're going to get into this a little bit later on, but and I don't like the analogy, but it is a bit, this is sort of where the art of machine learning and data science comes in, as opposed to the science. I don't think those things really, I don't think art and science necessarily sit on opposite ends of a spectrum. I don't think they necessarily oppose one another, but this is where there is a certain amount of finesse that you need to be able to read as a human that the actual training operation isn't going to provide you. So that's where an experienced a data scientist or machine learning engineer will have an advantage, and Kotib helps automate the workflow for picking those choices. If we look for folks who may not be familiar with what an ML workflow actually looks like, generally, we can segment these. These diagrams are all available on kubeflow.org, by the way. So that's the source for them. We can segment it into two phases. The first would be an experimental phase, which is identifying what you're trying to do, identifying the problem, and then collecting and analyzing the data. Excluded from this is the bulk of the of the time. I've had to explain to family members and others that programming, you spend 95% of your time stuck. Most of the time, we're not trying to reinvent the wheel. We don't have to develop some fun new algorithm. Something we think should be working is not working, and we're spending time debugging that. So let's call that a 1 to 19 ratio, right? Of time productively plowing ahead with our project and time trying to find an answer to what's not working. At least if you're a programmer at my skill level. In data science, it's worse. It's probably a 99 to 1 or 1 to 99 ratio, because cleaning the data, amalgamating the data, coalescing the data, getting access to the data, eats up a huge amount of time. So anything that we can do, and that's a hard problem. There's not a ton outside of bringing in more humans to help with that we can do. After all, if you had the ability to make decisions about your data, then your job would be done. That's kind of the point, right? So we really want to speed this up. Then you need to code your model, pick how you want the structure of the model to work. You need to see what kind of results you get. That's a sort of experimentation. You need to tune the hyperparameters, which we'll talk about in a second. Then you need to do this whole thing again. When it comes to production, it's a similar set of steps, but a little bit different. So we've coded, a mechanism for transforming the data into, there's a sort of industry standard term that for folks watching, if you're ever, if you ever want to be the person who sounds really educated, just, refer to what's known as a model ready data frame. You need to get the data into a state, into a format, into a form that the model can understand. You tell the model, this is what you should expect in terms of data coming in. So there's that. We'd like to automate that. That's where the notion of having a pipeline really makes a big difference. Then we have to train the model. We'll show that in a second. And then we have to actually serve the model. We have to deploy it in some way that we can see we can have other microservices or other services in our environment speak to the model. Ask the model a question. Say, hey, I've got Dave over here. He's his last 5 shows that he watched were X, Y, Z, ABC. I guess that would be 6 shows. And tell me what I should recommend to him next. And then over time, as more and more people choose not to watch Tiger King, or choose not to watch, don't pick up on those recommendations, the model is performing worse, right? Like that ship has sailed. So there is a process by which we must update, monitor the quality of the model's output, and then update it on a regular cadence. And indeed, there's lots of exciting work going on, and some organizations that are indeed using continuous learning, what's known as continuous learning, in production. So just to hammer the point home. These are the Kubeflow components that map to the different stages. You'll notice the data cleansing problem and data collection problem is left untouched. Oftentimes in the wild, for folks who might be interested, you'll see the what we used to call the smack stack, but now I guess it'd be the stack with Kubernetes instead of Mesos. But Kafka, Cassandra, Spark, these types of tools, streaming or batch, to be able to ingest large amounts of data, and then we can pass it into a process for transforming it. At the production level, you'll notice that pipelines span all of this, right? We would have in our pipeline could even have a transform data step. We would have a train model step. We would have a serving step and then a monitoring step as well. And here are how the frameworks line up there. So I'll take a pause, actually. I'm sure you have questions, Dave, or someone from the audience.
I love how you started with, it's just an endpoint that answers a question for you, and then you kind of look under the covers and you're like, oh shit, like there's like so many different moving parts here, so many different pieces of the stack and the architecture, and wow, there's an awful lot going on here. And I'm very excited to see just how Kubeflow is stitching all this together and making it better for people to consume. Because is this a standard machine learning pipeline? Like, 12 or more different pieces of software? It's complex.
Yeah. I used to joke, that Kubeflow is more complicated than Kubernetes in many ways, right? To have a functional Kubernetes cluster, let's see, what would you need? You need the API, right? So you need some control plane, resources, scheduler. You'd need, kube proxy, core DNS, kubelet. What am I missing, Dave?
That's pretty much it. The building blocks of a distributed applications would just be, I need networking, I need discovery through DNS, I need compute and a scheduler, and then let the workloads go and do their thing, and obviously an API to coordinate that. But I think what I didn't appreciate until you kind of walked me through these slides is, and I love the way you said you just start with an endpoint, right? That's just once the model is trained, but there's all of that legwork to get to that point. And when you had that graph and you're saying, well, some organizations, it's taken them 6 to 9 months and it cost them $500,000. And there's just so many different components here. And I'm assuming that's probably consistent across most machine learning workloads, is that it's the training and evolution of the model that is the bit that needs coordinated. And the faster you do that, the better velocity you've got at shipping new versions of that model is how you make your money. Is that fair to say?
Yeah. I mean, that's thank you for raising that. I mean, that's the between the lines message, right? It still pays significantly. It's still an ROI, deeply ROI positive endeavor to actually spend that $500,000. That's just in compliance costs, right? Yep. So that's not even including the labor time and the infrastructure and all the stuff that went into it. And you can see the impact of it. I mean, AI is everywhere. I'm using a camera application on my iPhone to serve as my webcam. Your telephone, or with the Apple architecture, it's got multiple special purpose cores on it, right? Some are neural cores, some are image processing cores. So there's a high speed and low speed CPU cores. This is everywhere. If I move my head, the bubble around me, you see, shifts, right? Like James Bond. Ooh, this is cool, James Bond. So how's it doing that? It's recognizing my face in real time. That's crazy and terrifying. The COVID vaccine, another perfect example. The COVID vaccine uses mRNA. mRNA is super unstable. That's why these vaccines go spoil so quickly, right? And need to be kept in liquid nitrogen and all this stuff. It's because the molecule degrades, and being able to predict where that molecule degrade transform the world, right? I'm very much looking forward to getting back into society when all of this blows over, right? Like, so it's everywhere. It's everywhere, you know?
Okay. Could
And
we?
the reason that, yeah,
Sorry.
go ahead.
I was just curious, like, obviously, right, so we're looking at Kubeflow today. This is a way to kind of, I don't know if it's to automate or orchestrate or just simplify all of these moving parts on Kubernetes. But what was it like before Kubernetes? Was it just the Wild West?
Oh, well, before Kubernetes, it's so interesting, I find in technology. Should we kill the slides for a second? Just chat this one out. I mean, I don't know.
Yeah.
Okay.
Oh, where'd your audio go? No, I'm not hearing anything. I think when the screen share dropped, it kind of cut you out.
How about now?
Oh yeah, it's back now. That was weird.
Okay, yeah, that's special. Yeah. I could see the little microphone bar. Yeah, what was it like? So one of the things that blows my mind is just how the left hand doesn't talk to the right hand, right? I mean, there wasn't a lot of distributed computing going on, but at the same time, there, everything was being done. There wasn't a lot of distributed computing going on, but it was possible, right? Like there were options for this. But the people who are working on these training and data science questions weren't talking to the people who were doing a lot of the distributed computing stuff, right? And there's certainly the people who were doing the distributed machine learning at that time, if you could even call it machine learning. I mean, you got to remember, a lot of these discoveries around machine learning are extremely recent. I mean, really in the last 10 years. Neural networks were, for 50 years, they were conceptualized in the 60s. For 50 years, everyone thought it was a ridiculous and impossible thing until somebody figured out, okay, let's do back propagation and it'll work. And there was a great article. Oh my goodness. I'll share a link with you, talking about the folks who the academic team who discovered that you could do deep neural networks, and with no product, they sold their company for in an auction for $50 million to Google. It's just like an acqui-hire, anyways. So it is, that's the one side is very new. On the other hand, the folks don't talk to each other. And then we also concurrently had hardware breakthroughs, right? I mean, this is I'm not a gamer personally, but the gaming world, we owe them a debt of gratitude in a way, because by purchasing high-end GPUs, they essentially subsidized the development of GPUs such that they became useful for machine learning, right? Which is something that I don't think most people really think about. So you had really, what you had is people, a confluence of events. One being, we now have internet scale data, right? We now have problems we want to solve that previously we didn't have the mathematical algorithms to be able to process in a way that would result in anything at all valuable, right? So, I mean, it doesn't matter if I'm not, if I want to have a self-driving car, if I don't have a machine learning framework or the algorithms to be able to produce something that will learn how to drive, I'm not going to even attempt it, right? And then we had GPU, right? And that really gave us a lot of horsepower. And the scale of these things, for things that are meaningful, GPT-3, which is an NLP model, got a lot of attention when it came out fairly recently. That, to train that model, required I'm not so good with electromagnetism. It was 3 gigawatt hours of electricity. Is that higher? That seems like a lot, right? That is a lot. It was 3 hours of a full nuclear power plant's output. Okay, so that's the meaningful metric by analogy for me. It's a lot, right? So these are computationally extraordinarily expensive operations, but the yield is there. There's a reason to do it, right? So that's really how I see it. We didn't really have a lot of distributed computing. People could get away with using really big boxes with a couple of GPUs attached to them. The objectives were less ambitious than they are today, if that makes sense.
Yeah, that does make a lot of sense. It helps solidify everything that you're saying and makes me understand it a little bit better. Just that evolution. You know, I can even think back as probably around 10 years ago as well, and everything, at least the organizations I was at, was all about ETL pipelines and doing everything in big batch machines at night when it was maybe cheaper, or using spot instances and stuff like that. But now, you know, with things like Kubeflow and TensorFlow and all this other stuff, we're more real time. We're streaming machine learning or training models, and I think that's probably driven a lot of, I don't know, change in the tools that we use as well. Like, it's not just here, send this zip archive to someone at 10 p.m. and they'll process it at 3 a.m. over 4 weeks, and then you'll get it back.
Yeah. Hey. Yeah, exactly. You know, I remember, you know, back in my Mesos days, you know, just to have a silly example, China Unicom was a huge and very public user of Apache Mesos, just as to go in the Wayback Machine here. And the reason that they made the migration to use Mesos was because when someone wanted to figure out what their cell phone bill was, they had to wait like 48 hours for a combination of batch processes and just compute time, right? And you know, that who would accept that now? Like, that's, you know, that's crazy. We would anytime I log onto my bank and they have a maintenance window, I consider getting a new bank. I consider getting it, like, inexcusable.
I do that with every company. If I see a maintenance page, oh, we're down for scheduled maintenance for the next 6 hours. I'm like, what is this? Like, that just gives me so much fear about the way that they handle their data, work with their data, and work with their systems. There's very few cases where I find that acceptable these days.
I refer to that as the onion ring and the French fry problem. I like onion rings. I like French fries. If I order French fries and I see an onion ring in my basket of French fries, now I'm worried about what's going on there. You know what I'm
saying? I like that. All right. So,
all right, back to it.
Yeah. Do you want me to pop out your slides back up?
Please do. Yeah. All right. So what's new in Kubeflow 1.3? I know we wanted to give a quick update. I'll just go through this. This is a big feature release that we're coming up to. So we've got new and updated UIs. So we have a serving UI now that's got integrated logging and monitoring. We've got a new UI for hyperparameter optimization experiments. We've got TensorBoard coming. This is the TensorBoard provides you with a monitoring, not from endpoint health perspective, but from quality of model perspective. If that makes sense. We talked about before, you know, don't keep recommending Tiger King. We have a way to manage volumes. A lot of these data sets are big. How do we avoid copying them a million times? And how do we get visibility into that? We have integration with an open source project that we call Kale. This is part of the stack developed by one of my colleagues here at Aricto in my day job, and better integration with pipelines. So all of this is being, you know, getting to the point where we've got so many people in production, you know, we really want to make this as easy and as clean as possible. We are also including, it's been out in the world for a little bit, but the ability to run VS Code in RStudio as your IDE. Like I said, you can, if it fit, you know, if it's containerizable, which what isn't, you know, then you're generally good to go. But this will come out of the box with new example notebook images for TensorFlow 2.0 and PyTorch. And then lastly, we've made some enhancements to KF serving, such as making it easier to do canary deployments. Super important, right? With a model in particular, because we're not, you know, it's different than the software development lifecycle where, okay, sure, we can, you know, put something in stage and use production, you know, anonymized production data that we pull back into staging. It's not, you know, the issue that we'll see with machine learning models, you'll see in a second, is that we don't really know what exactly is going to happen until we get out there, right? So you want to really take your time and roll these out progressively over time. and just some additional library support there. We've upgraded Istio. Istio 1.9 will be shipping. We've completely refactored the way that the Manifest Working Group, led by Yannis Arkadis, also one of my colleagues at Aricto, has completely changed the way that we deploy it. So it's pure customized now. You can deploy Kubeflow as of 1.3 with just basic kubectl. We've got multi-user pipelines, so now you can isolate pipelines appropriately for production deployments. And pod affinity, pretty standard stuff, but just making the sort of catching Kubeflow up to the latest and greatest, really, in the Kubeflow community. I mean, pod affinity is not latest and greatest, but we have to think about how we expose these knobs and dials from to an end user who is very likely unfamiliar with Kubernetes objects and deployment models. So that's the state of affairs with new stuff in 1.3. And I promise we'll be getting to a live coding example in a mo. But I wanted to describe a little bit about what the coding, just provide an analogy for what the coding example will be demonstrating. Because if it, code that makes no sense, seems of limited value. So if this is your first time being exposed to deep learning, I apologize that I'm the one to introduce you to it, but I don't have a PhD in anything, let alone mathematics. So if I can learn it, you can too. And I'll be borrowing an analogy from Andrew Trask's Grokking Deep Learning, which is published by Manning. Highly, highly, highly recommend it as a way to conceptualize and understand what we're actually doing here. So we are going to use an analogy of a fork analyzer. And what I mean by that is we are going to attempt to create a clay mold. You can think of it as a clay mold, a block of clay, and we're going to try and make a mold. And the mold is not going to be for the purposes of pouring liquid metal and producing additional forks. Instead, it's the goal of our exercise here is to produce a mold that has that anything that is a fork should fit into the mold, and anything that isn't a fork should not fit into the mold. Right? So the mold will tell us, is the thing I'm putting into it a fork? And the way it will determine that is whether the fork sits in the mold comfortably or whether it, gets bumped by the sides of the mold or something like that, such that it doesn't sit comfortably. Does that make sense?
Yes.
Okay. So I apologize for my heinously terrible graphic design skills, but it is what it is. So here's our clay mold. It's a block of clay, right? And I will use you as my my audience foil here. So David, tell me, do you think this is a fork? Are you smarter than a clay mold?
That is a fork.
Okay, so I would agree with that. And so what we will do is we will take this this rendering of a fork and we will press it into the mold. All right. So what's the outcome of that? Well, now we've got a fork-shaped mold, right? But it's this fork shape, right? So let's see how well our mold performs. What's next? David, time to shine. Fork or non-fork?
Fork.
All right, agreed. I think this is a fork. All right, so let's dip it into the mold and see what happens. Well, you can see on the screen that actually, if we put this fork into the mold would tell us that it's not a fork, right? It wouldn't sit comfortably in the mold that we've made, right? Correct. So the mold would say, this ain't no fork. We would say it is. So the mold goes, all right, fine. This is a fork too. All right. I will change my mold, right? The mold will change shape, right? As it's clay to accommodate this. You told me this is a fork. Fine. All right. It's a fork. I believe you, whatever. I'll change myself to accommodate this weird, I don't know, Victorian style tea fork or whatever it is. All right. So next up, fork or non-fork?
I'm going to stick with fork.
Agreed. This is a fork as far as I'm concerned too. But let's actually just take a second here and observe some differences. The forks that we've seen so far have 4 tines. This one has 5 tines. The forks that we've seen before all merge down at the base of the tines. This one has a perplexing gap. So if we were to put it in the mold, we would say, wait a second, this isn't a fork. The mold would reject it. So the mold has to update itself, right? As we dip it in, now it's going to make space in the clay to account for forks like this. Next up, fork or non-fork?
Definite fork.
Definite fork, agreed. What do you think is going to happen when we try to overlay it? We have to rotate it, right? If we put it in horizontally, it's not going to work, right? So now what we're saying to the mold is a fork is a fork regardless of which way it's presented to you, right? You need to account for different rotations of a potential fork, right? So we'll layer that in. And the mold at this point learns, so orientation doesn't matter, right? Like as long as I can sort of standardize the way that I'm observing these, as long as they have these characteristics, and you're starting to see with the overlay what exactly a fork looks like, right? There's a little bit of gap between the tines. There are tines. There's a part of the fork where it all merges together, and there's a handle, right? Let's look at another example. Fork or non-fork?
I mean, I guess technically it's a fork, but I want to say not a fork. But it's
so I for the purposes of this highly contrived example, it is a pitchfork, exactly. But you're right. I'm going to call pitchfork a fork. It has fork in the name. I'm not a linguist. Don't hate me. But let's see what the model would say. Well, the mold would say, nah, this doesn't fit in comfortably, right? This is not a fork. Okay, so now the model has to take into account a fork that has an odd ratio of length of handle to length of tine, right? And that would be different thing about a rake, right? That also looks like, but it's not, right? So think about that. So now the model says, David, you're killing me here, right? Does the handle even matter at all? And the model in this case is saying, I guess not, right? The thing that seems to be important are these tines and the fact that they come together and there's a little space between them and yada yada. It seems like the handle is irrelevant, right? So you know what? I'm going to ignore handles. I'm just going to chop a section of myself out so that any handle that comes, through, I'm just going to disregard that. Apologies, my dog is harassing me. I'm going to completely ignore handles. All right. Now, is this a fork? What do you think?
No,
but similar to a fork, right?
Yeah.
So if we were to compare this, the model would say, okay, yeah, that's a fork. From what I can tell, in order for something to be a fork, it has to have tines and it has to come together at the bottom, right? But that's actually not true, right? It must have a handle to be considered a fork, right? And there's some ratio of handle to tine length that we're not exactly sure what it is, but we know for sure you're telling me this isn't a fork, then I know I need to be looking at the handle, right? So the mold would say, it looks like a fork to me. The comb admits it, comes out of the closet, admits that it's a comb. And, the model then, says, okay, I need to consider the handle when evaluating, but apparently I don't really care how long the handle is, right? So this is the process. All credit due. Thank you, Solomon. All credit due to Andrew Trask, who wrote this book. Is a spork a fork?
I think we have to answer all the difficult questions today, don't we?
Well, it's so funny. So my girlfriend is a lawyer. She's gonna hate me for referencing this. My girlfriend is a lawyer, but she studied linguistics in college, and there was a Supreme Court case here in the United States where you're not allowed to destroy financial records, right? Like if the government wants to investigate, you can't just throw it all in a dumpster fire and say I don't have any records, right? And there was someone who was caught fishing and fishing fish that he wasn't allowed to fish, and he threw the not to put what I don't know, not illegal, I guess illegal. The fish he wasn't supposed to catch, he threw overboard before the police boat caught up with him. And so the government argued that a fish was a record, that you have thrown a fish out. And in this case, the fish is the record, right? But he would, his lawyers argued a record's a record, a fish is a fish. So these sort of ontological questions, these definition questions, are super important. And I think your comment highlights just how important it is to label things correctly, right? And to understand cultural perspective. Like, as far as I'm concerned, this is not a fork. But I don't speak for every person on planet Earth. I have no idea. Like, maybe this is a fork. Maybe this is a fork to somebody else out there, or maybe there's only one word, right? That exists in a language, human or extraterrestrial, to describe this object. So that the model only knows what you show it, right? And its universe is restricted to the data that you train it on. The images of forks being the data that we've trained it on in this case. Does that make sense?
Yes. Am I doing okay? Am I winning the fork game?
Yeah, so far you've done a great job. Yeah.
Okay.
Yeah, I would encourage you to take up data labeling if you ever have extra time. But you can see this is the challenge, right? How do we label data? How do we ensure that the data is labeled correctly? If I have a model that's continuously learning, how do I know that someone isn't feeding me a bunch of combs to attack my model? Now my model's going to start thinking that combs are forks. That's not good. So
is that something?
This is the analogy.
Are you okay for a question just now? Yeah, is that?
Please, yeah, as many as you'd like.
So I am putting this online as a quiz and encouraging people to answer questions to help me train my model, and there are bad actors that are throwing in bad data. Is that easy to identify and work with? Does that ruin the whole model?
Yeah. It does, and it is a challenge. So I'm trying to remember. I believe it was I have to remember the name of the podcast. It was. I don't think it was. It wasn't the Go Time podcast, but it's the same network of podcasts. Oh, thanks, Salman. Really appreciate the feedback. It's the same network of podcasts. Anyways, they had a very interesting discussion with some of the folks from Mozilla who are, Mozilla, really, you're doing really important work, and thank you. I'm sure, it's a challenge, but one of the issues is, there's really a dearth of material for like natural language processing in languages that don't have a huge community of speakers, right? So how they have a great system whereby essentially the labeling, people can contribute, right? Spoken versions of text that's read. And then that goes through a peer review process, if that makes sense, right? So people will double check to confirm that you're not attempting to submit bad data. The other resource that I would encourage folks to take a look at is David Aronchik, who's one of the co-founders of Kubeflow, currently runs open source machine learning over at Microsoft. He gave a KubeCon talk this past KubeCon, the most recent one, in which he spoke about different attack vectors and for machine learning models and ways to mitigate them. But yeah, if you're taking input from the community, I think we've seen that quite a bit with sort of the issues of news bubbles on social media networks, right? Where the stream of information, stream of news that gets the most reaction, continues to feed on, and it leads to extremes in perspectives and exclusion of counter perspectives. So yes, this is the ethics around AI are incredibly important, and everyone needs to pay extreme attention to them and be aware of who you're excluding. Think about this: if you're and I think 999 for you all, 911 for us, an emergency response. If you've only trained on people with native accents, right? 20% of America is foreign born, right? There's no guarantee that these, heck, we pronounce things differently. We speak the same language. So, these questions can't be afterthoughts. They must be preliminary thoughts, prerequisites to using this. So
nice. Yeah, I guess it helps to be Google, right? I mean, you can just launch something called reCAPTCHA, claim it's for security, but really you're training all your internal models. So.
Exactly.
Please click the one with the motorbike on it. So we do have a couple of questions. I don't know if you want to take them now, whether you want to take them as we go. I'll let you decide if they're appropriate for the moment, or if you're going to cover it later, just say. So Walid is asking, do you have any advice for people that want to run it on restricted networks on-prem?
Yes. Come to the Kubeflow on-prem special interest group meetings. Those are on Thursdays. We also have a mailing list, a dedicated mailing list that we use for our SIG. So George is helping us out too. So maybe he can share a link to that. Our meetings alternate between European friendly times and West Coast friendly times and Asia Pacific friendly times. They're on Thursdays. We would love for you to come join Kubeflow Slack. We have a channel there too, and we'll be more than happy to help you. As one of Jeff Fogarty, who's one of the co-leads of the special interest group and runs production Kubeflow clusters on premises for a big American bank, says if it's not behind the proxy, it doesn't count. So you will find lots of kindred spirits there. Let's see. I have other questions in the chat here. Happy to take them. Salman, great question regarding Istio. So the question is, why was Istio chosen as a service mesh for Kubeflow? I think that this is where the politics of open source come into play. Istio, obviously, a Google and IBM collaboration. And so I think that was the way to go. For a long time, also, I think Istio, Linkerd at the time didn't have a sidecar proxy model, and so it didn't get anywhere near the kind of performance that Istio did. It, had some scaling issues. Now they moved to a sidecar model, as far as I understand, and now everyone and their brother-in-law has a service mesh. So to the question of, are there plans to allow for different service mesh? Yes. And simply by asking that question, you are now mandated by law to come to our working group meetings, because we are working on with one of our technical co-leads, Marlo Weston, who works at Intel. We are spearheading an attempt to get service mesh interface implemented to allow anyone's service mesh a day in the sun, and to decouple in some way a dependency on Istio. Super early days. Do not get your hopes up. But that I think there's a lot of really exciting work going on in that regard too. So, yep.
Awesome. Perfect. Should we jump back to our forks?
We're done with forks.
We're done with the forks. Got it.
That was the whole kit and caboodle. So
I was just getting on a roll there. I feel like you've cut me off too soon. I was just getting the swing of it.
Listen, I can't decide if it would be a great job or a terrible job to, it's certainly not very stressful, but do I want to be a full-time fork analyzer? I don't know.
But if you sit and do like 30,000 of those in a day, and you click one wrong, and then you can't stop thinking about it, and you wake up in the middle of the night and you're like, what if I've destroyed this model by clicking fork? And it was like, a spark, and like, oh shit. Like, there were no rules on that. I not for me. Too stressful.
Okay. Yeah, no, I agree. Better to avoid any additional stress burden in your life. So just to let you know, I have up here an example of Kubeflow. Can you see that? Okay.
Yeah. Can you zoom in a bit on that? It's a little difficult to read on this.
Yeah. Let me see. Let me zoom it. How about that?
Let's go 2 more.
2 more? Okay. Fingers crossed everything works as intended.
Yeah, I think that's all right. If anyone has a problem reading that, just drop in the comments. We'll go more. But it looks okay for me.
Okay, cool. And just to let you know, I have clicked away from seeing the screen because I am 100% cheating on this live coding exercise. Because if I goof it, it's not going to be fun for anyone to watch. You try to debug it. So yeah, should we get started?
Yeah, let's go for it. Any questions come up, I'll keep you updated.
Yes, thank you. That's what I was hoping for. All right. So this is the Kubeflow UI. Every user has their own namespace. And that translates to, or a workspace, that translates to a Kubernetes namespace. Let's open up some notebooks, right? So I need an environment in which to start my development. So what can I do? I can give my environment a name. We'll give this, we'll call this X-ray. And I can pick an image that I want to use. I can also use any kind of custom image. Most people, will have an image that they're for a project, right? So your team is all sort of aligned on one thing. I can specify my CPU and memory guarantees. So this would be a request. There's no you don't really necessarily, for the audience that's going to be using this, the end user data scientists, you don't necessarily want to put a limit on it. That's generally sort of an administrative task. Let's see here. Oh, this is not. Give me my configurations. Oh.
Uh-oh.
All right. Time to go to our. No. We're good. We're good. Did I tell you it was cooking show style, or did I tell you it was cooking show style? So here's a cluster that's actually working. Woohoo! All right. So I have an example that stood up, but we're doing it live. And I got to zoom this one in, of course, because I did the same on the other one. And just tell me when to stop. How we look?
Yeah, I think that should be all right. Let's take it from there.
Okay, cool. Thank you for your flexibility. So let's call this X-ray 2. We're going to do the same thing we did before. We're going to give it a nice big drive. I think I have like 200 gig on here. So another 50 shouldn't hurt anybody. I can add extra volumes. I want to be able to interact with Kubeflow pipelines. I could also at this point specify whether I want to attach this to a GPU. I believe I have GPU in this cluster, but I don't want to attach it to a GPU because it's something I advise folks against, because most of the time the GPU is going to be idle. And the beauty of Kubernetes is we have shared resources. So make a pipeline, have one of the pipeline steps use the GPU, and then let other people use it, right? Does that make sense?
Makes sense, definitely.
All right. So this is going to take a second to come up. In the background, I am going to SSH into...
so what's this spinning up right now? Is this a virtual machine inside of Kubernetes?
A virtual machine inside of Kubernetes. Shame on you. You know it's not. No, this is... No, I know you're just trying to feed me the line here, but no. In fact, no, David, it's not. This is a container. This is a pod that's being deployed to my namespace, and there's a Jupyter. Like I said, it's going to be renamed a Jupyter Web Applications Jupyter controller that manages that. And if you'll notice here, there are configurations that I can apply. And this uses an object called pod defaults. I don't know how common the use of pod defaults are outside of machine learning and Kubeflow in particular. But suffice it to say, the way that this works is what I'm doing when I actually click this, one of these configurations, and that could be, for example, give me in this notebook, I want an environment variable that has access to, that has the up-to-date secrets for our private container registry or a private, Git repository or whatever we're doing within our environment, right?
Right.
So anything like that, or it could be, maybe I'm about to do some stuff that requires a specific type of hard disk at a minimum. So, you can access it that way. And what the pod default controller actually does is what we do with the Jupyter Web App controller does is it puts a label that that will be applied to the deployment, the stateful set that's actually being generated behind the scenes, all abstracted for the end user, GUI driven. But it will apply a label to that, and then the pod defaults controller knows to observe that label and then to inject a config map or a secret or anything like that. Either it's environment variable or it's a mounted, what do they call it, projected volume, whatever. You're making me dig into my like CKA studying. Like this is it's been a while since I took that test. Thank goodness they made it valid for 3 years now, though. It's a huge benefit.
I think that feature used to live as a pod preset back in the day before that was deprecated.
Correct.
I'm assuming it's now just an emission controller, and Kubeflow's version is called pod defaults, but it's not something I've used personally. At least the pod default version, I mean. But it sounds like the same thing as the old pod presets.
Exactly right. This is like a successor to that. Yep, exactly. Okay, so what did I do? I just clicked connect, and now I am presented with a JupyterLab environment, right? So you have a file browser, some plugins. We'll take a look at those in a minute. First things first, excuse me, I have to cough. First things first, we need to get our data. So in order to get our data, we need my Kaggle key, which I don't know where I put. Actually, I do know where I put. Oh, all right.
You can share it with us. You're very trustworthy here.
Yeah, I just don't want to shame myself with like. Let me pull up a Finder window here and drag and drop. Please hold. All right. So I need my Kaggle key. Kaggle is a great place if you're getting started with all this stuff and you want to get some good data sets to experiment with, yada, yada. Highly recommend checking out Kaggle. The other thing I'm going to do, just because it's really boring to go through it one by one, is copy in a requirements file. This is a Python notebook. So there we go, requirements. Okay, so I'm going to pop open a terminal. So this is like if you did kubectl exec-it-bash or something like that, same sort of thing. I'm going to do a few things first. I'm going to alias L. Oop. On Ergo Docs, be my friend. There we go. I'm going to alias L as ls-alh. Okay. All right. See, what can we see in here? I've got some environment specific stuff, from Jupyter specific stuff, nothing too crazy. First thing I'm going to do is put my key where I need it to be. So I got to make a .kaggle folder. I'm going to cp kaggle.json. Kaggle. There we go. .json to .kaggle. I don't know why it didn't autocomplete like that. All right, so let's l.kaggle just to make sure it's there, and it is. Okay, great. So next up, what are we going to do? We're going to do pip3 install -u Kaggle. That's going to give us the Kaggle CLI, which will be super helpful. All right, next up, we are going to download a data set. How about that? So we are going to do Kaggle data sets download. Download. What do we want? Okay, let me just copy the repo here.
Can you try pressing Command plus on that a few times and see if it zooms in?
Yeah, I think there actually is a way to change the console.
There was a presentation mode there. I don't know if that does anything though. Under view.
Oh, really? Where did you see that?
Just at the bottom.
Presentation mode. And that doesn't do it. No?
Yeah, just try Command plus. You on a Mac or are you on Linux, Windows?
Yeah. I'm on a Mac. Command, and I've got so many like modifier keys on the Ergodox.
Nobody that has an Ergodox and has come on this stream has had a pleasant time typing. It seems to be the way. He's like pain, you Ergodox users.
No. It is the best. But when you ask me to do something different than what I'm used to, I don't oftentimes. I have to remember. Plus, I use the Dvorak keyboard layout. I mean, that blew it up, but it's for the purpose. We'll zoom it out. How about when we get into the notebook? There we go.
Yeah, if we're not doing much on a terminal, if it's just getting dependencies, we can just move on.
Yeah, let me control.
I don't think downloading a YouTube URL is going to work with Kaggle though.
Not yet, anyway. All right. copy. No. All right, I'm just going to type it out. So this user on Kaggle is awesome, and you should totally check out everything that he's got on there, because these are some really fun data sets. So this time we are going to be trying to create an image classification model similar to the fork. But instead of predicting forks and non-forks, we are going to be looking at chest x-rays to determine if the x-ray presents with pneumonia or does not. And one can imagine many valuable applications for that, particularly say in remote places that may not have access to radiologists all the time, that kind of thing, or as an enhancement, double check to a clinical decision-making sort of a process. Next up, we're going to unzip chest x-ray. There we go. So you can see here, lots happening on the screen. Basically, the way that the images are labeled, that is to say, how do we know whether something is a healthy, normal image or a pneumonia image, is by the directory. And so the modern machine learning frameworks all have very useful helpers to just say, here's the the 0 and here's the 1, right? A binary outcome. Either this person's got pneumonia or they don't, right? Does that make sense?
Yeah.
All right. So next up, what we're going to do is just make our life simple by doing pip3 install -user -r requirements.txt. And we're going to go through all of this, and it's going to install all of the libraries and so on. Such a great, let me just open this up and edit it, because there is something that is not kosher. File, save file. Let's try this again. I like looking at this. It takes a second, but I like it because it just demonstrates so many people contribute stuff that's super important, that we all rely on, and we really build on the shoulders of everybody else, the people who have contributed stuff before, and it's what lets us do what we do. And so I don't begrudge it. I'll put it that way. It's like a good reminder to be appreciative for everything that's been invested.
Yeah, there's so much amazing open source software out there. Any problem you can think of, you can go to npm, creates, the Go registry, PHP, you search for it. Someone's generally done it for free, made it available, and it's there for you to use and hopefully contribute back to. But it always amazes me.
Exactly.
Open source is a wonderful thing.
Yeah. And there's libraries that everything in the world relies on, maintained by one lady in a basement somewhere, So it's incredible. It's a real free for all. Okay, so we've got our dependencies installed, our libraries installed. Now we will come over to the launcher and we will open a Python 3 notebook. Ta-da! How about that? I will give, of course, I mentioned Paul Timothy Mooney from Kaggle. I also want to thank the Coursera course by Andrew and his collaborators from Google. So this is where I've learned a lot, and it's all open source, but I want to give credit where it's due. I borrowed some of their techniques and a little bit of their display code here. So the first thing we got to do is import some stuff. So let me Jupyter has this weird thing where it really cares when you name a notebook, as to whether you end up with 10,000 files. So let's do import OS. We're going to import random. We're going to import NumPy as NP, import TensorFlow as TF, import TensorFlow.keras as Keras. So Keras is like a sugar layer on top of TensorFlow. Just makes your life a lot easier. Then we're going to get even more specific. We're going to say from TensorFlow.keras.optimizers. We'll talk about what these are. I even have, I tracked down a neat little GIF to sort of illustrate it. Again, thank you, Internet. We're going to import the RMS prop optimizer. And from TensorFlow.keras.preprocessing.image, we are going to import image generator. Okay. Oops, sorry, I misspelled that. It's image data generator. I'm 100% cheating. I find live coding in front of other people like the most stressful thing. Okay, so then we're going to do some other stuff that'll be familiar. We're going to import matplotlib.pyplot as PLT. We're going to import matplotlib.image as mpimage. Nope, none of that was correct. Mimpimage, yep. And then just so that we get so we get consistent results, we're going to set the random seed, just so we can do apples to apples. All right. And we will execute the cell with Shift Enter. No module found. Oh, because I missed a P. That's thing I always have to tell non-computer folks is that the thing about computers is if the computer says you did it wrong, it's because you did it wrong. I'm just going to copy and paste in. This is just, we're just going to look at the length of a directory because our images are in the directory. Right. Yep. And I just want to be able to use that to say, this is how many images we have. So we have 1,342 normals and 3,876 pneumonias. This is a very small data set. This should never be used for anything serious at all. But you'll see that we are still able within this context to, if we had 25 gigs of images, we'd have to check back next week, So,
is that a pretty normal ratio, like 3:1? Is that is that still the golden ratio for machine learning? Like if we want to do pneumonia detection, we need 3 of them to every 1 non-pneumonia, or is that just complete serendipity?
This is complete serendipity. To the best of my knowledge, the golden rule is more is better, more diverse is better, right? So, equally weighted among the group that you want to, the groups that you want to be able to make predictions for, right? So I believe, in fact, that this data set comes from, I want to say Vietnam, if I recall correctly. Suffice it to say, it's going to be a population of patients from Vietnam that may or may not be, applicable to everybody else, right?
Okay.
Does that make sense?
Yeah.
All right. So just keeping an eye on the time. There's I'm going to do a copy paste for the boring bits because I want to be able to spend time on the exciting bits. And here, what I'm going to do, this is a really handy technique that ever since I learned about it, I do it all the time, where we'll just define a base directory. We've got a training directory. So this is very helpful. Right. So among our training data, you can see here, it's all under the subdirectory train. You can see it over here too. Right. So here we go. Train, test, chest x-ray, train, test, and validation. So training is the data set we'll use to train on. The testing is to observe whether or not that, to keep some data outside so that the model can't cheat and update itself based on the forks we're going to test it against in the future, because then it'll learn about those forks, or in this case, the x-rays, and it won't be representative of new data that it's never seen before in the real world, right?
Yep.
So all I'm doing here is just a little directory manipulation. Okie doke. And if we add up the training for normal, so that we have 5,218 training examples and 624 testing examples. All right, so this will be used to validate. This is very handy that the data set comes like this. It almost never does. There are some really helpful helper functions that will split your data set for you. like the test train split, appropriately named test train split tool that comes with SciPy. So let's actually, let's be data scientists for a moment and take a look at some examples of what this data actually looks like. So we'll set an index for ourselves for comparison purposes. All right, and let's take a look. Let's call this normal, right? So we're going to look at a normal example. I'm going to give it an image path, and that's going to be got to join this up. Train normal dir. Yep, here we go. And then within that, I want train normal f names, and I want to pull the obviously the pick index. That's why we made it. Okay, and then it's a little hard to do with the zoom, but we'll get it. We'll get it. All right, we can scrunch this a bit. There we go. All right, so then what we're going to do is we're going to have an image variable and emp image. Remember, we made that variable up at the top. We're going to do imRead image path. And then we're going to do plot imShow image. I'm not a professional data scientist. If there's, folks who take offense to any of this, know that I do this very much as a novice. All right, here we go. So these are grayscale images. I'm displaying them in a sort of fun color, highlight way to make it just look a little bit different. But here's a person who does not have pneumonia. All right. So there will be a test at the end. Are you smarter than the model? Apropos the forks discussion earlier. So now let's compare that with a pneumonia example. And I've already, no need to watch me type poorly.
So feel free just to paste whatever. Like, yeah. If I have questions about the code, I'll just throw them at you. Don't worry about it.
Okay, cool. Yeah, sorry, I want to make sure we get through it. So anyways, okay, so we're doing this. Now we're doing it with a pneumonia example. Okay, looks pretty different. Sort of, I want to use the word gloopy, but I don't think that's a Scrabble accepted word. So
I was thinking more cloudier. Haunted. It looks more haunted.
You're thinking what?
More haunted.
More haunted. There we go. Yep. Okay, so I think so this is interesting, right? Like these are different cases, and this one is only barely more haunted, right? So not so super simple here.
So I failed already.
All right. You and me both. I mean, if I didn't go to data science graduate school, I definitely also did not go to medical school. So you put those two things together. It's going to be a nightmare for you and me over at the hospital. Some people are going to die. All right. So what am I doing here? This is how we use Keras to construct a model. So we're creating a variable model. It's going to be a sequential model of type Keras models. And what we're defining here is a couple of things. The first thing we need to do is give instructions to the model about what kind of data it can expect. So, these are 3 color channels. My bad. Okay, so these are color images. So the first thing that we're going to do is we're telling the model, hey, you're going to get an image. It's going to be 150 by 150 pixels, and there's going to be 3 color channels. So for every pixel, there'll be a value for each of the color channels. Then what you're going to need to do is sort of unravel that, right? And so it's a flat thing. But the first thing that we're going to do is we're going to do this is a convolutional neural network. So what's a convolutional neural network? Basically, it's like applying a filter. I'm going to show you an example of what the model sees a little bit later on. It's very similar. You can think of it very similarly to like the way that your phone, will put an image, we'll put a filter on an image, right? We're looking at the pixels, we're seeing the values for each of the color channels, for each of the pixels, and we're making some decision about how to adjust it based on the pixels that surround it. Okay, so you can imagine there's lots of different types of, they're called kernels, that lots of different types of filters, right? So here we have a 3x3. So we're passing, you can think of it like, when folks used to look at slides over a light box, and they would scrunch in, to look, and then they would go, across it to really look very closely at a slide image or a photo negative. There's a very similar idea. And here we're going to do 16 different filters. And the filters will be 3x3. And then based off of the output that we get, where we adjust, the input will come in with its own values for those pixels. And then the output will be based off of how those pixels relate to each other. So here we're doing, for example, max pooling. It's a two-dimensional image. We're doing max pooling, which means that it's going to evaluate the filtered result, right? So it might say, whatever the algorithm is that's applying to that 3x3, those 9 pixels, and it's saying, take the max 2x2 of those. Find the max values, right, for those for in a 2x2 for that, and use only that. Then we pass it into another layer where we're actually doing another layer of convolution, right? So here we're doing 32 filters, again 3x3, and then we're going to pool it down to a 2x2, and we go through that one more time. After we get through, we'll talk about activation in a second. After we get through all of that, what I want to do is then flatten this out. So I'm getting an array of values, right, that are between 0 and 1, typically, some normalized values, and then I'm going to put those into a neural network with 512 neurons. So you can think of this as every neuron is a dense network. So every neuron is connected to every other neuron. And essentially, the way that machine learning works is it'll push it through, observe which of the neurons contributed the most to the error that was observed, right? So, which neuron was responsible for calling this, if it makes a mistake and says, I think this person is healthy and does not have pneumonia, it'll then recalculate, right? Just when we got a new fork, we had to recalculate the mold. It'll recalculate in a process called backpropagation that by virtue of partial differentiation, we'll be able to associate the end result, namely the error, how bad the prediction was, how off it was in terms of its confidence that this person was symptomatic of pneumonia or had pneumonia, which neurons contributed the most to that error. And so we're going to change those neurons in the opposite direction the most, and which neurons had relatively no impact on the decision or on the error, let's leave those alone, right? Does that make sense?
Yeah, I think so.
Okay. The activation is just, what does it take for this neuron to actually fire, right? Like we don't want every neuron to fire all the time. There should be some minimum of signal that the neuron's receiving in order for that to even be considered at all by the end result. So ReLU is a contraction of rectified linear unit, if I recall. So you just think about like it almost looks like a call option graph. So nothing, don't give any signal, but if you get past this threshold, then have a linear relationship with output to input. Sigmoid, if you remember from school, is going to give you like an S shape, right? So far extremes will never go above 2 bounds, but as you approach 0, you start to see a significant increase and then leveling off of the slope of the curve. All right, does that make sense? Sort of.
It's good just going.
Feel free to ask me any questions.
No,
it'll make a lot more sense once we see an example of it, right?
I hope so.
What the model sees, yeah. So, sorry.
No, but it's doing stuff. You're explaining it well. It's just not something that I am familiar with. But I'm looking forward to seeing the step by step through it. So keep going. Let's do it.
It'll make more sense. This is why I picked a CNN with images, because you can see what the model sees in a way. All right. So here I'm going to create two image data generators. This is the handy helper functions I was talking about before. And then we're going to give it some information about batch size, how much we want it to automatically resize each image. It's a binary class in the sense that you either have pneumonia or you don't. We're going to define batch size here. It's going to error on me because I did not, in the interest of simplicity, I did not include this, but we're going to include it. Going to define some variables known as hyperparameters. Let me copy and paste these in. We'll talk about these a little later, but I just wanted to have these variables in memory so it doesn't whine at me. So we're going to define a batch size. We're going to define a source directory and so on. Now, you didn't realize this, but if I may go back to the fork example, we made some significant choices when going through this whole exercise. One of which was that after every fork, we made an adjustment to the model, right? Which is okay, right? But may not be actually what we want, right? Like we may want to average all of the forks, right? Let's not change the model. Let's take the average of the changes to the model suggested by the multiple forks that we've looked at in a batch, and then make changes based on the average suggested by that batch. Does that make sense? Like you don't want to go too overboard. Otherwise I'll get a model that's like, Victorian T fork and pitchfork, right? Like maybe I can average them together. That'll give me a healthier sort of look. That's batch size, right? The other thing that we didn't talk about at all is, like, for example, what kind of sand are we using in our clay? Clay is made from sand, right? How thick are the grains, right? If they're coarser, I will have less ability to, I'll have less ability to create fine detail. But maybe that's good, right? Like maybe I don't want the model to expect these sort of Baroque design features of a fork, right? So this is the same idea here. This is how we define the nature of the mold, if you will. All right, so we've got this going on. Now we need to compile our model. All right. And what we'll do here is we'll just call the compile function, and we'll use an optimizer called RMS prop. And basically the optimizer says, okay, I can calculate, you'll tell me how I'm going to calculate loss, right? Tell me how I know how wrong I am, right? In this case, we're going to use a loss function called binary cross entropy, which is a way to measure how off binary classification examples are. But like now tell me like how I should actually adjust myself based off of that. Like, should I go really fast in the direction like of finding a minimum to my error? Should I go slower? Do I want to have momentum? Right? Like there's lots of things that we can take into consideration for the way that the model should update itself, for the way that the mold should update itself. Right? All right, so we'll compile this. Now here we go. Now comes the fun part. All righty. So we are going to define a variable called history. I remember finding this to be like a really weird sort of thing, but basically you can think of it as like the tape in a cash register, right? And we're going to call a fit exercise, and what that's going to do is it's going to train on the training data. It is going to use the test data for validating that, and we're going to train it for a certain number of epochs. So how many times through the data do we want to iterate? And there are a bajillion different features, like different ways you can things you can specify within this. Like you can do, my goodness, there's like an unknowable amount. You can have callbacks to stop training based on something that happened. Let me just kick this off. You can have if you minimize your loss to a certain level, you can have you can introduce skew. You can have a holdout data set that only gets used at the end. I mean, there's lots and lots of different things that you can do when you're fitting a model. So what are we doing here? So this is a training process. You're observing it in real time. So here are the number of they're called steps. So the number of processes that are occurring, and the number of batches that are being flowed through. Here's our loss function, right? And here's our accuracy. So at this point, the model is 67% accurate, now going up to 68. And how many epochs did we decide to? Lots of, this is the sort of finesse part. So we're doing one epoch here. Okay, that's fine.
So just in like really simple terms, that because this has been seeded with images that knows have pneumonia and images that knows that doesn't have pneumonia, it's a looping over them, applying the model, and then the back propagation is when it gets one wrong and it knows it's wrong, it feeds it back through the model, tweaking the parameters until the accuracy.
Even if it gets one right. Yes, exactly right. Exactly right. And thanks to the beauty of calculus, we know which neuron, which signal propagator was the most responsible for the problems, and which one was irrelevant. And so the beauty of tools like RMS prop as the optimizer is that they can account for that difference in scale, right? That difference in impact, in order to adjust on a per neuron basis exactly what exactly how much to adjust the formula for propagating signal for each neuron, right?
Right.
So I push one through. It's a pneumonia. I correctly predict that it's ammonia. Good. I want to encourage my model to use that as a thumbs up. Like, whatever you just did was good. Use that a lot, right? Like, use those are the signals you got to be looking for in terms of pneumonia, right? And then it'll go back and make those changes, make them more ingrained. Right now, I go forward, I find out that I goofed up. Okay, well, I'm going to come backwards and adjust that so that my loss, my error is smaller. All of machine learning is just reducing your loss, finding your data, picking a good loss algorithm, way to calculate loss, and then trying to make that loss smaller. That's the ball game, right? Does that make sense?
Yes.
Yeah. So what we are observing here is highly characteristic of machine learning exercises. And that is that we have a loss. Let's ignore that for now because it doesn't really mean a whole lot. And we have an accuracy with the training data. And the training data is 75% accurate. Not bad, right? I mean, I don't know anything about X-rays. I don't know anything about the not abstract algebra, linear algebra that's sitting behind this in terms of how the tensor flow is optimizing the tensors, tensors are just multi-dimensional matrices, how it's doing all of that. I have no freaking clue. But I myself, as an end user, have now created a model that is not 75% accurate, but 70% accurate. So remember, we split our data into testing, to training and testing. And the training data was given to the model to picture Rocky, okay, I'm going to learn from this, right? And then we, here's the big competition. It's not your standard sparring partner. These are images you've never seen before, right? And here you can see that my accuracy on my validation is only 70%, right? And so oftentimes what you'll see, let's actually run this for a few more epochs to make the point even more apparent. And we'll continue on while this is running. We'll do 4. A GPU would have been nice, but I didn't want to overcomplicate things. What you'll observe is very common. It's known in if you've ever heard this term, overfitting, which basically says, I am excellent at predicting the 4 forks that I've seen. You give me one of those forks, I'm going to crush that. Like, no way I'm screwing up those 4 forks. You bring me a rake, I've never seen it before. As far as I know, it's got the right, the world is different than what I've been trained on, right? So it is highly possible, like here you can see, it is highly possible to get incredibly high accuracy in your training data, but it's so specific to your training data that, I don't know, a fork from somewhere else in the world is not going to get recognized as a fork, even though it's a fork. That makes sense. So this is where we were talking art and science. This is where an experienced data scientist will be able to, see very quickly, like, wait a second, you're telling me I got 92% accuracy and I have like a data set of 5,000 images. This is overfit. This is basically memorizing this data set and not generalizing to X-rays of people with pneumonia or not. Right? Does that make sense?
It does make sense. Yes.
Okay. Cool. I may actually want to interrupt this because this could take a hot sec, but it's okay. We can do other stuff in the meantime. All right. So next up, I am going to just copy and paste in some visualization stuff. This is not, overly exciting. And then once that runs, the above cell runs, then we will be able to see some output here. So let me queue this up. And then here we go. So the first thing we're going to visualize is the relationship between the epoch will be our x-axis. Then we will observe accuracy and loss, and then validation accuracy and validation loss, right? And so we'll be able to see what we'll observe almost assuredly is that look here, right? Here, I've got validation accuracy of 72%, and I've got training accuracy of 93%, right? And what you'll observe is that, it'll start to memorize that training data set, but in fact, our validation accuracy, how well it works on data it hasn't seen, will in fact, at a certain point, start to go down because the model is overfitting. The model is too specific to the training set, and it is picking up on things that are in fact not generalized qualities of a pneumonia patient, but rather these specific 5,000 people's idiosyncrasies.
Is it fair to say then that the data set is the most important part of building out these models, or
Oh yeah, for sure. The data set is everything. In fact, there are new it's really exciting. I mean, this might, if we watch this in 5 years, we might be, it'd be like trying to encourage someone to program COBOL these days. Like we may look like absolute medieval, dinosaurs. And the reason for that, I mean, there are products on the market. Apple produced one for their software development kit. I forget what it's called, but basically the entire thing is a UI, looks like any Apple design product that has 2 boxes: drag test data, drag category 1 here, drag category 2 images there. And then you don't see anything about it, and it produces a model. The reality is that even though this type of very specific evaluate, the tuning, the model structure, how many layers, what kind of convolutions, should it be dense, should it be ReLU, sigma, all these sorts of details are far less important than the data set, which is to say that you could have way more performant models with a bigger data set as opposed to like, what is the impact of like fiddling with your model architecture or like the associated stuff. Now, it's still valuable areas of research, but it is really, really, really all about the data set. There's another one that I saw recently. I think it's called MindsDB, where it's imagine a SQL database where you say, okay, I made a table, and here are the features, so the parameters or the details about the row, and here's the outcome, right? So think of a silly example like an e-commerce example. Here's the SKU or the product ID of the first thing this person bought, second, third, fourth, and here's what they bought fifth. So I want to be able to predict with 4 what the 5th one is going to be. So you just like tell it, like, give me another column that is predict 5, like, and it'll just do this all behind the scenes. And in particular, in Kubeflow, there's some great automation around this as well, which we'll see in a second, to be able to evaluate things programmatically. That's why I've defined things like, epochs, learning rate, and batch size as hyperparameters to fiddle with that. And I really want to do a demo of this, but it's possible to fiddle with your model architecture too, right? Like you could say, put in another layer, remove a layer, add more neurons, less neurons. Those could be variables that you could experiment with also.
How specific? Can you scroll back up to the convolution and the thing? Like, see, there's like 12 lines of code that is this the main bulk of our model? And how specific is that to detecting pneumonia? Like, if I were to throw a different set of images at it, like, a football and, a golf ball, is it still going to be the same pattern? Do I have to tweak what I'm changing in the code? Like, how does that work?
Yes. So you would not have to, you could throw any binary image classification, that has 3 channels and could be, resized reasonably to 150 into this. There's nothing at all special about it. After all, if I did it, it can't be that special, right? Like I literally, and like I'm not a specialist in this. But you would have to retrain the model, right? So you couldn't take an extant model and use it for as is for footballs and I wanted to say like footballs and soccer balls, but I think you probably meant a soccer ball in the first place. So why don't we say footballs and baseballs? And and you would have to then do. You have 2 options. Either you can just take the raw model and just train it again, just basically point this notebook to a different set of directories, or you can do what's called transfer learning, which is in many cases, what we're doing here is nothing more than passing a series of filters over stuff, right? And then observing the output. So then with transfer learning, and this can be very expensive, right? With transfer learning, what we do is imagine you just stuck another layer on the bottom, right? That said, yeah, okay, start with the model as it exists, right? Because it's a pretty good model for 2-dimensional images. I like it a lot. I don't want to pay the compute and time and hassle to redo everything associated with that model. I might not even have a chance to. It might not be possible for me. I might not have access to the source data. But I have this new data set, and it is a binary image classification. So I'm going to have it hold this set of manipulations constant, and then just fiddle with the new stuff that's underneath. Don't only change that. That's called transfer learning.
Okay, awesome.
Yeah,
we got a question there which I'll throw up just now, even though I think our epochs are just about done.
Yep.
Albin asks, how did the 512 neurons get matched to the flatten out pixel array? Do each neurons get assigned some pixels?
Let me show you. So you see here, there's a flatten layer. That's what did it. And yes, so it got flattened out. It basically just, take, I'm trying to think what would like a Lego, basically take a block off the top, put it over here, take the next block off, put it next to it, flattens it all out, just a bunch of numbers. Those numbers go into a neuron. A neuron is just a formula, like a y equals mx plus b type of thing. The B is your bias. The Y is your, the M is your slope, and then the X is your input value. And then all of the neurons are connected to all of the other neurons. So based on the back propagation, some will be elevated, some in terms of their signal amplification, some will be muted, right? And as a result of that, the model learns what neurons indicate what outcome and at what to what degree.
Nice, thank you.
Mm-hmm.
Do we have some?
There's a great YouTube video.
Sorry to go.
I can recommend. No. There's a great YouTube video that does a fantastic job visually animating all of this process. So anyways, here we go. Let's take a look at some visualization. So we started off unusually high. The seed obviously updated as this was our second time running through it. But what you observe is that there is a significant delta, right? And we got very lucky on this fourth run through. We got a higher accuracy than in any previous. But typically, what you see is that there is a decline over time. And this is the loss. So just the inverse of the accuracy, not the exact inverse, but accuracy is success, loss is failure. So you can see that the curves point in the mirror image way. Does that make sense?
It does.
All right, great. So now let's get to sort of a look at what is actually what is the model actually seeing. So here we go. So these map to our layers, right? So what did we say? We wanted 16 different filters passed over the image. Okay. And here we can see that this is a pneumonia example. All right. So what we're doing, we're passing a filter over it. And then we're passing, we're taking the max pool of that and then passing that 32 filters over it, if I recall correctly. So let's see what happens. Here you can see that the pixel height here is like 75 or something, right? Then when we condense it, when we pool it, we're only picking the loudest of all the pixels in that filter. And as a result, our image shrinks. And here you can see that I've got 32 filters running across this, but it's a smaller image. And then I'm going to do that exercise again. And now you can see that the scale is getting smaller. Here's the max pooling result of that layer above, right? And what you notice in the same way that the fork mold changed over time by virtue of what you plowed into it, you see sort of the same concept here, right? Where we're observing certain commonalities among these things where it seems as though, for example, if I were to summarize, there's a certain vertical pattern, right, that is associated in these examples. And in some cases, they're vertical on the side. In some cases, they're vertical in the center. And in some cases, they're completely blank. That's also helpful to know. Is this using, I think this is using a random input. Let's just make sure. Yes, random choice. All right, let's run this again. Let's see if we can get a normal. Okay, so here's a normal. Okay, so what do we notice here at the very bottom layer? I hope it's big enough for folks to see. But what I see here is that rather than the vertical line standing out quite so much, I'm starting to see more horizontal lines that seem to sort of line up with the ribs, right? With the rib cage. And it's certainly not nearly as pronounced, the vertical lines in here. So this is what the model is seeing, and this is what it's using to make a determination based on all of the outputs that it sees here, what classification it should be in. So yeah, that's the ball game. This is actually using the model that we just trained. Let me find it for you. It's in here somewhere. We are actually plugging this into the model. If I could just find the line that is doing it. Oh, it's here somewhere. It's so zoomed in. Oh, here we go. Successive feature visualization model. So we got the model and we're asking it to predict X, right? So it's taking an image example, manipulating it, normalizing it, doing everything we did, and then it's plowing it through the model itself. And this is what what the model is seeing. So you're really, quite literally seeing what the model is seeing. I know we've kind of been on the air for a long time. I could show you how to turn this into a pipeline. This has been sort of a data science primer, less so a Kubeflow primer. Up to you.
If you have the time, yeah, we can do that next step. Let's see how we move this over.
Sure, yeah. In the words of the late, oh goodness, come on, not now. I'm trying to remember his name. Mitch Hedberg. Anything's in walking distance if you've got the time. Okay, so this is Kale. Kale is an open source tool that basically normally the workflow, what you would have to do is you'd have to take all this code, you'd have to take it out of the notebook, move your imports into every cell, make each cell its own function, then use Kubeflow pipelines, domain-specific language, DSL code to write the pipeline. Kale says, you don't want to do any of that. We'll give you a button. You click the button. This is what's happening here. So you'll notice I have this like handy dandy little pencil icon. That's an overlay. So I can call this, I can define what's going on. So this is an import step, right? Okay. Now in a pipeline, I do not need to do any kind of printing of output, right? So this will skip this. This is my hyperparameter cell. So I'm going to call this my pipeline parameters, AKA I want it to like goof around with this, right? Like I want it to adjust this, to know to adjust this automatically. We'll see how that goes. Again, batch size, how many forks do I want to flow through the mold before I make changes on my model? All right, and we're going to put this down to 1 epoch just because time purposes. Train faster. All right, so now I'm come to my first pipeline step. Not a super exciting step, but we'll call it something like pre-process data. And it doesn't depend on anything. You can specify, resource dependencies also, but it doesn't depend on any other pipeline steps because guess what? It's the first pipeline step. Next up, matplotlib inline. This is definitely a skip. The pipeline, Kubernetes doesn't care about seeing a picture, so we're going to remove these. Yep. Okay. Then we've got, why don't we call this the compile model step? After all, we are compiling the model. And it depends on pre-processing the data. No great surprise there. Okay. Now we move right along to our training step. So we'll call this train. And it depends on compile. Woohoo. All right. And then below, I just want to make sure I remove all of these and just skip them so that we don't end up with complaints from the scheduler. All right. Now, the last thing I want to do, because I do want to use hyperparameter optimization, automatic hyperparameter optimization, is I have to tell the, the Kotib, the hyperparameter optimization software that comes with Kubeflow, needs something to shoot for. So what do we want to do? Rule number 1, we want to minimize our loss. Cut down on the loss. If we've got loss, it means we're doing something wrong. So we want to find the version of this story, the version of the model that has the most that has the least loss. So I'm going to give this a name. I'm going to call it X-ray. So these are all Kubeflow CRDs actually for your ops folks on the line. So an experiment is a CRD, a pipeline is a CRD. Give it a description, and they have relationships with one another. Like an experiment may have many pipelines, that kind of thing. Or a pipeline may have many experiments. I don't know. It's all. That's the problem with visual tools. You never know what things are actually called. All right. So now what I want to enable is hyperparameter tuning with Kotib. So what I will do is define the search space. So it noticed that learning rate was something that I had defined, right? So that was one of the hyperparameters. Let me close this and take you right back up. Where did I define this? Right up here in the pipeline parameters, right here, right? So it's going to automatically pick that up from that cell. And it's going to be a range. Let's say on the one hand, 0.001, and max, we'll say, I don't know, 0.1. And let's go crazy. Let's say that we go in steps of 0.01. All right. So the learning rate says, okay. Once you figure out how to change the mold, don't go crazy with changing the mold. Figure out how much you think you should change the mold and then divide that by 100, right? Or 1,000 in this case, and go incrementally from there, because it is very easy to overshoot the runway, so to speak, on that and end up in on the wrong side of a gradient descent. Epochs, we can manipulate this. We're not going to because we don't want to change the amount of time it takes to run this thing. We're going to have a batch size min of 8. Let's call it a max of 128, and let's go crazy and say, I don't know, 32 is the step. So let's go that way. We can define the algorithm for how it should pick different hyperparameters. And it's smart enough to sort of look back and see what seems to be working. And then what's our objective? We want to minimize the validation loss. All right. So I'm going to dial this down to 6. We'll have 3 parallel trials. Again, Kubernetes. This is where we get all of the Kubernetes goodness coming to life. But, thank goodness someone who's not familiar with that and doesn't want to learn it doesn't have to do their job. And now what Kale is doing is validating the notebook. The backend I'm using for snapshotting with Kale is Rawk. And once this snapshot completes, it's a fairly sizable data set, so it may take a second. There's quite a bit of blocks to look at. What it's going to do is it's going to compile the notebook into Kubeflow DSL code for me so that the Kubeflow pipelines knows what to do with it. Then it is going to upload the pipeline for me, hopefully. Then it's going to create an experiment around that. And then it is going to create a Kotib experiment whereby it breaks out each of the different, you'll see it for each run, it's going to pick, okay, try batch size this, learning rate that. It'll pick it'll determine which are the combinations it's going to run with first. So here we go. It compiled. Oh, cache control. API. Oh, I know why. Haha. Why don't we give this a different? Yeah. Duh. Let's make it a new experiment. X-ray 2, pipeline description, X-ray 2. Let me close this. Let me compile and run. Naming things. What a disaster. All right. And then we'll be able to observe this running.
Does it matter that your new experiment doesn't have a name?
Probably, yeah. I thought I saw it had a name. All right, let's third time's charm. Does it matter that it doesn't have a name? Yes, it matters, David. Would have been very helpful if you would include me into this.
I'm just kidding. Watching. I'm just here to.
Oh yeah, this is great. Oh, look at this. This has never happened before. I'm so glad it's happening now. This little jitter here. I don't think it likes being blown up to this extent.
I'm not surprised. I mean, it looks great on our side. Just FYI. So.
Good.
Okay, so what's this gathering suggestions stage?
Aha. So this is what I meant before when it's like making it has to make a decision, right? We're doing 3 parallel trials. No trials have run yet, right? So what should I use as my wacko combination of hyperparameters to kick this bad boy off, right? I have to make a decision on that. Okay, so this, I'm gonna zoom out just a scooch here because this is a little aggressive. Here we go. All right, so what is it doing? So for these 3 trials, it is going to vary the batch size from 8 to whatever this is. Let's find out. From 8 to 40 to 72. All right, and each one of these will be its own pipeline. So I can go ahead as a data scientist or data engineer. I can click on this. And here you can see my pipeline is running. So the first thing it did was the create volume step. I can click on any of these steps and see the logs for the pod. I can see the pod spec, the pod YAML. One area that I think folks who are looking for ways to contribute, please jump in, is to sort of simplify a lot of the stuff that gets thrown in here. And you'll also note that, the way that it's containerized is just powering this all through to, as a text file to the underlying image, which like maybe not like long term, it might be something that we want to, as a community, sort of work on. But we're waiting for the pods to come up. I can actually show you what this looks like from the terminal. So let me do a clear on this. I know it's a little bit smaller. Bear with me. Let me do a watch kubectl get PO. This is going to be launching in my namespace. So here you can see these are the pipelines that have that are waiting to get scheduled. Here are the ones that are running X-ray 2. This set of hyperparameters will get its own sort of identifier. And then here are the ones that that are waiting to run. So each of these is a pod. You know, you'll see similarities between the unique identifiers. That's because a lot of the you know, for this one, it might be that only one only one parameter is changed. So for this first batch of 3, they're going to have the same 5-character identifier in the middle here. Where's my pipeline? Actually, here we go. You wanna boot up here, bud? Do I have something that's got a little more action? Experiments, HP tuning, running 3. Trials, running. Are you though?
Is Kubernetes lying to you?
Maybe, yeah. Welcome to my life. Let's go back and just let's look at one that actually ran before, which I deleted so that I looked cool. That was a mistake. All right, here we go. Here's one that I didn't delete from that UI. Okay, so here's my DAG. I'm going to simplify it. So yeah, here's all my steps. So I can click into them. I can see the logs. I can see, you know, all the other stuff. And here is my training exercise. You can see the same loss and accuracy metrics that we had before. So suffice it to say, the operational benefit of using a tool like Kubeflow, and Kubeflow is the leading open source Kubernetes native platform for this type of work, is that now as a data scientist using Kale, rather than delivering a Jupyter notebook, which is sort of like a jail for my code, right? It needs to come out of there to be useful. Instead, I can deliver a scalable and repeatable pipeline that can then be iterated upon, chained onto, branched off of, to advance the project. And in fact, we could have a serving component at the end of it as well. And I, you know, in that, here's an example is a different model, but here I have a model that's being served just off the end of a pipeline. And I can see the logs for it. I can see the predictions that are coming out, as well as the input data that's coming in. And I have metrics. This is all new in 1.3. My colleague Kimonis and some of the other folks in the working group contributed this. So yeah, this is what greets the eager data scientist looking for adventure.
Awesome. Thank you very much. Will I pop us back over to video mode?
Yeah.
Awesome. Can you still hear me? Can I still hear you, actually? That should be the question based on earlier. No, I can't hear you. Oh, you're muted. No, you're gone. Is it your end? Do we think? All right, but I can't hear you. You know what? Okay, that's frustrating, but we are at the end of our session. I just want to say thank you very much. I think that was amazing how you managed to take such a complex subject, and you know, you didn't just introduce us to Kubeflow and the new features, but you actually took us on a full journey of data science and how we can apply that to real world situations like detecting pneumonia and x-rays. I found the whole thing riveting. I've learned so much. Thank you very much for that. Kubeflow looks amazing. I hope other people have really enjoyed today's session and will take a look at it too. So Michael, Although you can't say goodbye, there we go. We salute will do perfectly. Thank you very much for joining me today. I will speak to you soon. Have a good one.